Case Western Reserve University's Great Thinkers series proudly presents the Origins Science Scholars Program. These lectures are presented by the Institute for the Science of Origins, a partnership of Case Western Reserve University and the Cleveland Museum of Natural History, with the generous support of Richard Morrison and the assistance of Case Western Reserve University's College of Arts and Sciences, MediaVision, and WVIZ PBS and 90.3 WCPN IdeaStream. Welcome to the Origins Science Scholars Program, a series of talks on current research topics in origins sciences. Hello, my name is Glenn Starkman, Director of the Institute for the Science of Origins, and I am pleased to serve as your host for the series. The talk you're about to watch is entitled Quantum Mechanics and the Universe. As you will soon learn, it was probably quantum mechanical fluctuations in the early universe that led, through the action of gravity, to the formation of galaxies, and thus ultimately to us here today. In this talk, which I am pleased to deliver, we will learn about why we need quantum mechanics to understand our universe. Please enjoy the talk. So you've learned a little bit about quantum mechanics. Now, if you don't understand it all, don't worry, because Richard Feynman told us that if you think you understand quantum mechanics, then you're sorely mistaken. It's a very hard thing to really understand. It takes years before you even get an intuition for it, and even then, to have a deep, I don't think it's not clear that anyone really has a full, deep understanding. We don't completely understand quantum mechanics yet. There are many things about it that we're still puzzling about, and some of the things I'll tell you about may get to a little bit of those puzzles. But tonight I'd like to tell you about quantum mechanics and the universe. So, really focused on two things. First is quantum mechanics in the universe. And I'm going to be talking about inflation, has nothing to do with the fact that prices go up. I'm going to be talking about quantum mechanics and the origin of structure. And by structure in the universe, I mean us. How did we get to be here in a universe like ours? And the second thing I'm going to talk about is quantum mechanics of the universe. Partly, how did the universe begin? What do we know? What crazy thoughts do we have about how the universe began? And how does quantum mechanics play into that? Okay. So to do that, I have to start with some basic cosmology on one foot. Okay? I'm not quite as good as the flamingo at standing on one foot, so you'll excuse me if I put 2 feet down while I give you this lesson on one foot. And start with the fact that the universe is expanding. Okay? So that's a very basic fact, and those of you who are in the fall, we talked a lot about this. The universe is expanding. This is a really lousy picture of what it means for the universe to be expanding, because it suggests that it's expanding into something that may or may not be true. It's not important that it is. What's important is that the objects in the universe, like galaxies, are moving away from each other. We look out, we look in every direction, and if we look at objects that are far enough away, where the light has taken more than a few million years to get to us, we see that those objects are all moving away from us, and the farther they are from us, the faster they're moving away. And that is exactly what we would see if the universe itself were expanding, carrying the objects in it away from each other. Now, it's not that we live in some special place over here where we just happen to be living in the middle of an explosion. Anyone, we believe, anyone in the universe looking at would see the same thing, very much like if you had some raisin dough and you were living on one of the raisins and allowed the raisin dough to expand, to rise. If you looked out, you'd see all the raisins moving away from you, and the nearby ones would move away slowly. The further ones would move away more quickly. It doesn't matter which raisin you sit on. Well, you're a raisin, you happen to be sitting on the Milky Way galaxy, but someone sitting on another galaxy would presumably see the same thing. Okay? Now, we also believe, because of this, that the universe used to be hotter. And that's because when things expand, they get colder. And here's my favorite picture illustrating this. It's a plane that's just gone through the sound barrier. There's a shock wave caused by the plane going through faster than sound. And behind that shock, the air has expanded, and the expansion causes it to cool, causes the formation of a cloud. So we can see it very visibly here, the fact that when you expand a gas, it cools. can also see this if you go to the gas station and take the little nozzle that puts the air into your tire and feel it after you've let some air out. It'll be nice and cold because of the air expanding. It's how many refrigerators work. Okay. So the universe used to be hotter, kind of like this object, the sun. So the sun is about 1,000 times, the surface of the sun is about 1,000 times hotter than the universe is today. And you'll notice several things about the sun. One is that it's hot, but the other thing is that you can't see through it. So if you look at the sun, which I don't suggest you do, but if you did, you wouldn't be able to see right through it. That's not surprising to any of us. We wouldn't expect to. The reason you can't see through it is the particles of light called photons, they reach the sun, and there are charged particles in the sun, and those particles scatter the light. Well, the universe, right now we can look through the universe, but when the universe was a lot smaller, it was also a lot hotter, and all of the stuff in the universe was ionized. The electrons were separated from the nuclei, and so the photons, the particles of light, were bouncing around in the universe, okay, unable to travel freely. And then as the universe expanded, got cooler, the electrons became bound to the atoms, to the nuclei, formed neutral atoms, and then all of a sudden those photons, the particles of light, could travel through the universe freely, and they have been traveling through pretty much freely for over 13.5 billion years. And we're able to detect them. Now, we look at this. I told you that the universe used to be very hot, okay, just like the surface of the sun. And we want to look at the sun. We typically don't use microwave antennas like this one. Instead, we use optical telescopes that give us, or we use our eyes. We can't see the light from the early universe with our eyes because as the light traveled through the universe and the universe expanded, it stretched the light so that the light itself became, instead of visible light, which oscillates very rapidly, it became microwaves that can be detected with microwave telescopes like this one that was first used to see the glow of the early universe. Okay. Here is a map of what the early universe, of what the universe looks like when we look out with microwaves. It looks really boring. It looks the same in every single direction. Absolutely the same. Well, as we'll say, not quite the same, but very, very close to the same. Its temperature is about 2.5 degrees above absolute zero. Professor Matur talked last week about absolute zero. It's the lowest temperature you can reach. We're close to 300 degrees above absolute zero in Kelvin units. This is only 2.7 degrees above absolute zero. That's the average temperature of the universe today, and it's the same temperature in every direction. In fact, it is unreasonably the same in every direction. Why do I say it is unreasonably the same in every direction? Well, when I look out in that direction, and I look at this microwave light, and it's coming to me, it's been traveling through the universe for 13.5 billion years, and it just arrived here today. I pick it up with my microwave antenna. I look out this direction with my microwave antenna. The light has been traveling through the universe for 13.5 billion years. It just arrived here today, this moment, at my microwave antenna. And the temperature, or the energy, distribution of energies of the light coming from over there and the light coming from over there are almost precisely the same, to a part in 100,000. That would be like we got 100,000 people to walk into this room, and before they came into this room, I said, bring a glass of water. And then we stuck a thermometer, and every single one of them had exactly the same temperature water. Okay? Even if they had gone to the same water fountain, by the time 100,000 of them had filled up their glass of water, there's not a chance that that water would have been exactly the same temperature. Right? So how did the universe know to have that region over there where that light came from 13.5 billion years ago, and that region over there where the light came from 13.5 billion years ago, be the same? Because they couldn't have possibly sent a message from over there to over there. Because the message from over there, traveling at the speed of light, won't get there for at least another 13.5 billion years. In fact, if a message had been sent from over here, it would have just reached there now. So there was no way for those two places to come to the same temperature. That's a great mystery. Okay. And the only solution we know of is that the universe used to be not just much smaller. After all, I told you that the universe is expanding, and so it used to be smaller than it is now. It used to be much, 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 with lots and lots of muches, smaller than you would have thought. So that those two regions over there actually were touching each other in a sense, so that they were able to exchange information, so that it's like dipping water from the same well. So that's our only known solution. So here is our story about the early universe. Once upon a time, the visible universe was much smaller. And while it was smaller, it got homogenized. It came to the same temperature. Then something caused the universe to expand exponentially fast. Places moved apart faster than the speed of light. And the universe got very cold and very empty. Now, I know you think we can't move faster than the speed of light. We can move faster than the speed of light as long as we don't get caught. Okay. So the good news is that two places that are moving away from each other faster than the speed of light can't see each other doing it. So they can't exchange messages about it. And that's what's really not allowed. That's what would spoil our notions of past and present and future and causality. So it's okay as long as they don't get caught. Okay. And so we think that that's what the universe was doing. It was expanding at this exponentially growing rate, and the universe in that process got very, very large, very cold, and very empty because all the things that used to be close together were now all of a sudden very far apart. And eventually this stopped. The universe was refilled somehow with almost homogeneous matter, and normal expansion resumed. And we call this story inflation. Now, what could possibly drive this strange process of accelerated expansion? It isn't matter. Matter slows down expansion of the universe because gravity pulls. Right? If I let go of this, it's going to be pulled towards the Earth. Ordinary matter slows down the expansion of the universe. Dark matter slows down the expansion of the universe. In fact, our best and simplest bet for what explains accelerated expansion is nothing. And I don't mean that we don't know what could drive accelerated expansion. What I mean is that nothing, or the vacuum of space, which is a more poetic way to refer to it, is what we think drives the accelerated expansion of the universe. And the thing about it is, this isn't your grandmother's vacuum. It's the quantum vacuum. So here is where quantum mechanics comes in and tells us that the vacuum is not the same thing that we think of. We think of the vacuum of space as being something that has no interesting properties. Here is a good picture of the vacuum of space, right? It's empty, except for those words, the standard picture of nothing. That's what we would think the vacuum of space looks like. Boring. Well, here is a better picture, a quantum mechanical picture of nothing without the words. It's full of stuff going on. We learned a couple of weeks ago about the uncertainty principle, that we couldn't measure the momentum of a particle and its position equally at both to arbitrary accuracy at the same time. It turns out that there's another uncertainty relation, not as fundamental, that if we want to know the energy of something really accurately, we have to measure it over a long time. If we measure it over a short time, then we don't know the energy very well. And that means that we can break energy conservation for short periods of time. The more we break it, the less time we have to do it. And so really a better picture of nothing is kind of like this, with stuff popping in and out of existence all the time. And that means that nothing is very different than apples. Because with apples, if I have a box of apples and make the box bigger, I still have the same number of apples that I started with. On the other hand, if I have my grandmother's nothing, a box full of my grandmother's nothing, and I make the box bigger, I still have nothing inside it. But if I have a box of quantum nothing, and I stretch the box like the universe is stretching, so if I take the box of nothing and stretch it, then all of a sudden I have much more nothing for free. Now, that doesn't make sense if nothing has no properties, or it's not interesting if nothing has more properties. But if nothing is something, if empty space actually has energy associated with it, then more growth means more nothing, and more nothing means more growth. And this compound growth is what we call inflation. And so now we have time for some questions.
Glenn, how do you know the light arriving, you mentioned, is 13.5 billion years old?
What we really know is that we have a very good theory to explain the properties of the universe. Okay, this is called the Big Bang theory. We only know that it's 13. So what the Big Bang theory tells us is that we should see such light. Okay, it predicted that we should see such light. It also predicted other things like how much helium there is in the universe versus hydrogen, and how much deuterium and lithium. And those all tell us certain things about the universe. And in a moment, we're going to see pictures of the universe that have a lot more detail than that kind of very smooth picture. The details of that picture will allow us to date the universe, the statistical properties of the light that we see. It's not each individual photon, but it's actually the collective properties of the patterns of the light over the sky tell us that the universe, tells us how old the universe is, how fast it's expanding, what it's made of, how many particles of ordinary matter, how many protons and neutrons there are for every particle of light, every photon, things like that. So by detailed studies of the statistical properties of that light, comparing that to our theory, which seems to work very well to explain those statistical properties, we learned that the universe is 13.5 billion years old. Turns out that's also consistent with the fact that when we look at the oldest stars, we can look at collections of stars called globular clusters. And they turn out to be, well, for a while we thought they were 15 or 16 billion years old. That was a problem, because then they were older than the universe. But it looks like they are kind of a little more, 10 to 12 billion years old, maybe 13 billion years old. So they're around the same age. So there's a number of things, but the main thing is looking at the properties of this light in the universe and realizing that the universe is about 13.5 billion years old.
How do we know that we're seeing to the farthest edge of the universe, and that the light we're seeing would then be 13.5 billion years old? And if we know that, do we actually know where the Big Bang was?
We don't know that we're seeing to the farthest edge of the universe. In fact, in most versions of the way we think about the universe, there's a lot more universe beyond where we're seeing. All we know is that we are seeing back to a specific time. So as we look out in space, we're also looking back in time, because the light takes time to get here. And so that means we're looking back to times when the universe was hotter and hotter and hotter. Okay? And when the universe was about 1,000 times smaller than it is now, which was about 13.5 billion years ago, it was too hot for for ordinary atoms, neutral atoms, to exist. They were smashing into each other, being smashed into by light. They became a plasma, like the sun. And so the light couldn't travel anymore. So we're only seeing back to that point. Now, then we could ask, well, how much farther back in time is there? That's a complicated question. The simple answer is about a few 100,000 years. The more honest answer is somewhere between a few 100,000 years and some huge amount of time that may even be infinite. Okay? So we don't know.
Thank you for joining us. My name is Glenn Starkman, and aside from being the director of the Institute for the Science of Origins, I am professor of physics at Case Western Reserve University and director of the Center for Education and Research in Cosmology and Astrophysics. And I am pleased to be telling you today about the role of quantum mechanics in the universe as a whole. For more information on the Origins Science Scholars Program, please visit the Institute's website at www.case.edu/origins. /origins. In the first part of my talk, I gave you a quick introduction to cosmology and explained how the quantum vacuum drove faster than light expansion of the early universe. In the second part, we will learn how small fluctuations in the evolution of the vacuum led to the seeds of structure in the early universe. Gravity then took those seeds and turned them into galaxies like the Milky Way galaxy in which we live. Now we return to the lecture.
From that vacuum energy, that energy of nothingness, comes everything. And it's kind of like this. Here's a picture where I'm showing here how much energy we have. Okay? And this little dot represents the properties of the vacuum. We give it the name inflaton, okay? The particle that is responsible, the field that's responsible for inflation. And what's going to happen is that the amount of energy in the vacuum, in each little piece of the vacuum, is going to slowly decrease for a while. Okay? But it's very slow, and the energy associated with that change is negligible compared to the total amount of energy stored in a piece of vacuum. And that turns out to be driving this accelerated expansion that we call as inflation. And then all of a sudden, the properties of that inflaton change as it changes its value. And it falls down this kind of hill, and all of its energy turns into particles. And those particles spread out through the universe. That process is called reheating. So we have this period of inflation where the universe is full of slowly changing vacuum that has a lot of energy associated with it. Then all of a sudden, when the inflaton gets to a critical value, it releases all that energy and turns it into ordinary stuff: photons, electrons, quarks, which are the particles that make up protons and neutrons. Okay? That's how the universe got full of stuff again. Now, the thing is, that vacuum that I showed you changes in subtle ways with time and place, because there are quantum mechanical fluctuations. In other words, the amount of energy in the vacuum can change by a little bit as long as I do it for a short amount of time. So really, a better picture of the vacuum is more something like this. Look carefully. You see that there are small changes in the vacuum. They're hard to pick up, but they're there. Let's look at them again. Can you see these little small changes in the properties? You have to look really carefully, but the vacuum is fluctuating even as it's dominating the universe. So really, instead of this inflaton smoothly changing its energy, what's really happening is going along, and sometimes it jumps back up. Now, an ordinary classical field couldn't do this. But the inflaton, because it's governed by quantum mechanics, as it's rolling down this hill, can suddenly jump up a little bit and then do that again. We'd find it really strange if we saw a car rolling down the hill and all of a sudden it jumped up the hill a bit before it kept rolling down. But that's because cars are really big. Okay? If cars were quantum mechanical, if cars were only made of one atom, then they could do that too. Okay? And so the inflaton does that. As it rolls down, it sometimes jumps up before it finally cascades over the hill and releases all that energy into the universe. Okay? But those fluctuations are random. They're going to be different here, than over there. They vary from place to place. Okay? They're kind of like a roulette wheel. See, the thing about a roulette wheel is the game of roulette doesn't change. Every time you go to the casino, if you do that, you'll get a chance to do that in a year or so. Every time you go see the roulette wheel and they spin it, the rules of the roulette wheel don't change, but the results do. Right? In fact, I've set up this slide like that because I never know exactly how that slide is going to appear. So let's watch it again. So watch how the words come in. This time they came in like that. Here, let's do it again. This time they came in like that. Completely random. The rules governing how they came in didn't change, but each each time it's done, it changes subtly, according to the same set of rules. And so it is with the inflaton. So over here we have the inflaton behaving in some way, and let's watch what happens. So the inflaton's rolling down, but when exactly it jumps back up changes. So this one falls down a little bit before that, and that turns out to mean that over here there's more stuff left by the time the inflaton everywhere has fallen. Most of the stuff here is diluted away. There's only a little bit, and the stuff here, lots is left. And so that's a denser place in the universe than somewhere else. So there's a little more nothing here and a little less over there, and we can see that with this telescope. This telescope is called the Wilkinson Microwave Anisotropy Probe, or WMAP. And it sits 1.5 million kilometers, about 1 million miles, straight out from, on a line from the sun to the Earth, straight out, another 1 million miles. That's a really good spot because the 3 bright objects in the sky are all one way, behind its back. Okay? So it can look out into the universe with the sun, the Earth, and the moon behind it, and this is what it sees. Remember, I told you, it's going to see a very smooth map, really boring. But the trick is, because it's able to look out really, really carefully, it can actually make a much better map that looks like this. And right now, there's an even more advanced satellite called the Planck satellite that's going to make an even higher resolution map. What you're seeing here is the places where there was a little more stuff left over from the inflationary reheating, a little less stuff left over from the inflationary reheating. And you might say, so what? Well, the so what is really important. So here's a place where there's a little more. Here there's a place where there's a little less. But with gravity acting over time, this is what happens. The places where there is a little more, they get even more dense. The stuff attracts each other, and that turns into things like galaxies. Okay? And clusters of galaxies. In other words, it turns into us. So it turns out that we are all nothing more than gravitationally concentrated quantum flotsam. I know you don't feel like gravitationally concentrated quantum flotsam, but it's truly amazing. And what's amazing is that this theory seems to predict really, really well what we see out there in the universe. Okay? So if I go back and study this picture, a little while ago, someone asked me, how do we know that the universe is 13.5 billion years old? This is the picture that's telling us that. We're able to look at this picture and we're able to say, wow, look at the size of the smallest kind of features. There's some big features and some little features, but there are some smallest features. How big are they? How big are the most prominent features? Well, they're about a degree. Why is that interesting? Well, it turns out that in the early universe, when it was still a plasma, when it was more than 1,000 times hotter than now, there were sound waves traveling through that plasma. Okay? Just traveling freely through that plasma, oscillating in the plasma. And what we're seeing there are actually the imprints of those sound waves. Okay? Now, the largest sound wave that could have traveled through the plasma would have traveled about that far. From the beginning of the universe till the end, it would have traveled across the diameter of about 1 degree. Okay. By looking at that size, we learn about the shape of the universe. We learn about, by looking at how big those are, by looking at how bright those are, we learn about the shape of the universe. We learn that the triangles in the universe add up to 180 degrees. You probably remember that from a long time ago. The sum of the angles of a triangle 180 degrees. That's true on a piece of paper. It's not true on the surface of the Earth. If you take a triangle, if you start at the North Pole, walk south to the equator, turn right, go for a while, and then turn right again and walk back to the North Pole, you've just made a triangle. You've walked straight the entire time, so you have 3 straight sides. But if you add up the angles of that triangle, if you think about it, they add up to more than 180 degrees. That's because the surface of the Earth isn't like a sheet of paper. It's not flat, it's curved. One of the big questions about the universe is, is the universe flat or is it curved like the surface of the Earth? By looking at the size of these, we learned that the universe is flat. Appears to be very flat. Within 1%, if we want to ask how big is the radius of curvature, how curved can it be? The answer is that the size of the sphere would have to be many, many times the size of the distance that we can see out to. So the properties of this map have changed cosmology over the last 20 years and made it into a precision science, one in which we are able to learn things to fractions of to a percent, to a few percent, and over the next few years, we hope, to fractions of a percent, to answer questions like, what is the shape of the universe? How many particles of ordinary matter are there? How many particles of dark matter are there? How many neutrinos are there in the universe? And what was their mass? All of these questions we get to. So far, the most important tool is by looking at this light, which is coming from the changes in the inflationary vacuum from place to place in the early part of the universe.
How do these principles of quantum mechanics affect our understanding of dark matter? Can the same be applied?
So dark matter, we haven't talked about dark matter in this course so far. Dark matter is when we look at galaxies. So here we had a picture here of a galaxy. Okay? And we look at this galaxy, and we look at how fast the stuff in the galaxy is spinning around, we find that it's spinning around too fast. What do I mean by that? I mean that the gravity of the stuff in the galaxy isn't enough to hold the galaxy together, and so the galaxy should fly apart. Okay? And now you could ask, well, why doesn't it fly apart? And the leading explanation is that there's more stuff in this galaxy than we see. And that extra stuff can't be made of ordinary protons and neutrons. Okay? It has to be made of something else, and we call that something else dark matter. And then the question is, what is dark matter? Okay? And there are many possibilities. Okay? For a long time, we tried to make dark matter out of this stuff. Okay? So for example, we tried to make it out of things that look like Jupiter. Jupiter is really dark. I know we see it pretty well because it bounces light off the sun, but if you threw Jupiter out into interstellar space, we wouldn't have a hope of seeing it. Or for a long time, we wouldn't have had a hope of seeing it. Now we would have. Okay, so we know that it's not things like Jupiter. We know that it's not things like black holes. We know that because we can look at the light that's traveling through the galaxy. And if it was things that was black holes, like the size of the sun or bigger, then we would have seen the bending of light by those black holes. We would have seen what's called microlensing, lensing of background stars by that. So we think that it's probably particles. And in fact, we have a couple of people in the back who spend much of their time trying to look for the most likely candidate for those particles called weakly interacting massive particles. So those are particles whose mass is about 100 times the mass of a proton. Okay? And if our theory is right, they are traveling through your body. There are billions of them every second traveling through your body. Okay? Now, there are other particles that we know of that do that, neutrinos. We've measured neutrinos coming out of the center of the sun, coming out of accelerators. There are, I think, billions of neutrinos passing through your body every second. Okay? They don't bother you because they are so easily able to pass through very, very large distances of ordinary matter without interacting with it. The same thing with dark matter. So how do you find it? Well, the good thing is that there's a lot of it. Okay? There's a lot of particles, and very occasionally one of those particles will hit something and heat it up. Okay? Not very much, so you have to look very carefully. One way is to take a crystal and cool it down to near absolute zero and watch the rise in temperature. Another is to take many kilograms of liquid noble gas, liquid xenon. This is what they're doing, and they're putting liquid xenon at the bottom of a mine in South Dakota, and they're looking for the flash of light that will happen when the xenon gets hit by these particles of dark matter. Now, I still haven't told you what quantum mechanics has to do with it. These particles, single particles, are governed by the laws of quantum mechanics. I've told you in many ways about the least quantum mechanical of the particle candidates. There's another candidate called the axion that behaves in a very quantum mechanical way. It actually behaves a lot like the Bose condensate, the superfluid that Professor Matur talked about last time. Okay, so or like the light in a laser.
You mentioned being able to add up the sides of a triangle and showing that it's 180 degrees. What sort of experiment do you do to add up the three sides of a triangle?
The experiment we do the question was how do we, here we go. I went the wrong way. How do we see the sides of a triangle are 180 degrees? The answer is that we know the distance to these points, okay? And then we look at the size of these points, and that gives us three sides of a triangle.
Gives you one side of a triangle.
No, it gives us three. We know the size of that because we know the age of the universe at that point. We know the distance. So it gives us, we have two sides of a triangle, then we have the third side, and we're able to measure the angle. And those are the three sides of a triangle. So the question is, the comment was, that would be true if it's planar, but we're actually able to show that it's planar. We can have a longer discussion after if you like.
We hope you've been enjoying the Origins Science Scholars Program lecture on quantum mechanics and the universe. In our first two segments, I told you about how quantum mechanics in the universe affected its evolution. In our final segment, we will learn about quantum mechanical ideas for the birth of the universe. Now, back to the talk.
About quantum mechanics and the universe. So now some time for some wild speculation. You may be saying, haven't we just been having wild speculation? And the answer is, believe it or not, no. So we really understand quite well what I've told you. We understand quite well the physics of inflation. That doesn't mean it's absolutely correct, that this is absolutely for sure the right theory of how the universe behaves. But the evidence is slowly accumulating that it is, in fact, the correct theory to explain what went on in the early universe, the origin of structure in the universe, why the universe is so smooth, why it has the amount of stuff in it, why it's as old as it is, why it's as flat as it is. All these properties seem to be remarkably well explained by this theory of inflation. Okay. What I'm going to tell you about now, we have nowhere near that degree of confidence in it. So I'm going to try to answer questions that speak to the I tell you things that speak to the question of where did the universe come from, what is the universe, and what can quantum mechanics tell you? And we don't know. That's really the answer. But there are some daring, educated guesses, all of them, or pretty much all of them, related to quantum mechanics. Okay, so this is just kind of Alice in Wonderland journey through some of the thoughts of some of the leading scientists who think very deeply about these things. So you might ask, isn't quantum mechanics for very small things? Right? When Professor Matur is telling us about quantum mechanics, he's mostly talking about things like atoms. Okay? At best, he was talking about small buckets of fluid. Okay? But then it was really surprising that small buckets of superfluid needed quantum mechanics to be just for a good description. Now I'm telling you that we're going to apply quantum mechanics to the whole universe. Well, part of it is that the universe was probably once very small. That is, unless it's infinite. See, there it is, bouncing around according to the laws of quantum mechanics. You might ask, doesn't quantum mechanics describe what happens when external observers observe systems? That is really how quantum mechanics was set up. The whole history of quantum mechanics was looking at things like the hydrogen atom, looking at buckets of superfluid helium or superconductors or other systems where we get to observe them. We're standing on the outside. They are described by a wave function that describes the statistical properties of what measurements of those systems may yield. We make a measurement. The wave function collapses into a particular state. So the wave function changes. Now, we're living in the system. What does it mean to describe the universe by a wave function and to apply quantum mechanics? And the answer is yes, that's true, but maybe we can use it for an internal observer or a meta, i.e. some sort of imaginary external observer. We're not really absolutely sure how to do this, but that won't stop us from thinking about it. So we don't always know exactly how we're going to make things work before we try them. And so when people work on quantum cosmology, they are extending the boundaries of how we apply quantum mechanics. So here's, for example, a basic feature of quantum mechanics, and that is that in quantum mechanics, objects can suddenly appear where they weren't. We saw that in my pictures that I showed you of two particles all of a sudden appearing out of nothing, then disappearing together again. It's also true that if I could put a quantum mechanical pen on a very thin quantum mechanical sheet, after a while I'd have to catch it underneath, because it would go from being on top, all of a sudden it would appear underneath and fall through. So things can go from one place to another without going anywhere in between, okay, in quantum mechanics. Okay. Because the wave function, if you like, can leak through this plane. It can leak through this barrier without the object itself, in a sense, traveling through in the way that an ordinary object like my fist would have to travel through this desk to get to the other side. So, for example, objects can all of a sudden appear and then disappear in quantum mechanics. Okay. So here's wild idea number one. The universe appeared quantum mechanically out of nothing. You've asked me, where did the universe come from? Okay. What was before the Big Bang? And one of, actually two of the proposals, okay, to a quantum cosmologist, they're very different. To us, they're close enough to be the same, is that the universe appeared quantum mechanically out of nothing. So, and it's not really even right for me to say at some time there was no universe and then there was one. Okay? Because that assumes that there was a before the universe. Okay? So all of a sudden there's a universe there. Now the universe isn't fully formed. We've discussed how all these structures in the universe form, but the universe itself could form out of nothing. And you might say, well, how is that possible with quantum mechanics? How is that possible that all of a sudden there's this huge universe there? Doesn't that violate all sorts of conservation laws? And sort of a hand-wavy way to understand it is that if there's no total energy associated with creating the universe, then I can violate energy conservation because it's not violating it for an arbitrarily long time. Okay? And you might say, well, isn't there energy associated with the universe? And the answer is there's a balance of positive and negative energy, and those may be very, very, very close to zero. So a universe could last an infinite amount of time if it doesn't cost much energy. And that really leads us to this question of what was before the universe. And in this context, that's very much like asking an explorer who reaches the South Pole, well, what's south of you? And you might say, well, that's a dumb question. South is just this convention we have of how to put lines on the surface of this sphere. Right? We draw lines from north to south, lines of longitude, and we draw lines from east to west, lines of latitude. And when we get from the top, when we get down here, this arbitrary kind of point down here, we say we've gone as far south as we can. So if I ask you what's south of there, the answer is, well, my coordinate system doesn't allow for me to go south of here. That was just a useful way to tell me where I was on the surface of the Earth. In the same way, our notion of time may just be a useful way to put coordinates on the universe. And there may be no time below the South Pole. There may be no time before the beginning of the universe. Time itself, in other words, is created. Time itself appears, is part of the universe. It's a property of the universe, not of the theory in which the universe emerges out of nothing. So the universe, there may be nothing before the universe. Wild idea number two. Actually, the universe is one of many universes in a possibly eternal multiverse, a large collection of universes. Okay? So when we say the universe, what we mean is, what do we mean by that? We have to be careful. There's a lot of slippery concepts here. So by the universe, we might mean everywhere that we can see. Well, we already don't think that that's everything, because after all, if we went to the farthest place that we can see, we could imagine that there's someone else there, and they can see farther, right? And wherever that person can see to, well, someone could be standing there and they could see farther. But imagine the chain of all such people extending everywhere. Okay? We might call that the universe. All the places that we could see, and all the people we can see could see, and all the people they could see, and so on and so on. Okay? But that might not be everything. There may be other universes, other such collections of observers who can see each other. And those other universes, and we would call that collection, we would call a multiverse. And the universes of that multiverse may be connected to ours through some way that can't be seen, or they may be disconnected and produced by quantum tunneling, kind of like that other idea that universes appear out of nothing. So there may be lots of universes appearing out of nothing, and we can't connect from one to the other. Or it may be kind of like if you have take a piece of plastic like a balloon. I know I used to do this when I was a kid, and you take it and you go, and you make a little bubble, right? And then if you twist the bubble, you can actually get the bubble to break off, leave the other part, and you'll have a little bubble there. Well, it may be that in many ways, this process of inflation in a little place, if we imagine we have a region here that all of a sudden start to inflate, it could kind of like blow a bubble. That would be a universe that would actually, in some sense, separate off from the universe around it. And then we would have universes like this is called eternally self-reproducing inflationary universes. It could be that these universes, the way to get to them is through our dimensions, or it could be that you have to go off in some other dimension. These other universes could be real. In other words, there could be whatever that means. I'm not sure what that means. Or just some useful story that we tell in order to try to understand the universe. So here's a very simple such example, where here we live on this universe, and if we could just figure out how to go this way, we would find some other universes. And we could try to study these universes. In fact, some people have suggested that there are other such universes very near us, really close. If we could just figure out how to go, instead of this way, some other direction, we would find another universe. And there would be matter in that other universe that we would only see by gravity. And we would call that dark matter. So that's one very depressing form of dark matter. It's very depressing because there's probably no way to see it in detectors like our friends are building and putting in mines in South Dakota and other places around the world. We've seen it the only way you can, through its gravity. Here's wild idea number 3. The universe is actually an island in a very large, mostly empty, eternal, something I might call a megaverse. And in that megaverse, there are very rare but large quantum mechanical fluctuations that become universes like ours. So here's a picture of that. Okay, so we have nothing, and then there's these things that appear and kind of fly apart, and we happen to live in one of them. Okay? And sitting here, we're not able to see out to that other stuff that was out there. Let's just play that again. So we started with this empty space, very cold, very empty. All it's full of is nothing. I'm not showing you the nothing. Okay? But it's a very quiet nothing. It's slowly making the space expand. And then occasionally, universes, regions of higher density, appear, where the nothingness all of a sudden fluctuates quantum mechanically, and so that there's a lot of stuff. And that looks a lot like our universe. And you're living here in that. Okay? Now, the interesting thing is, we actually see that very slow accelerating expansion happening again. You may have heard people talk about dark energy as opposed to dark matter. What dark energy is just another period starting. We see once again that the expansion of the universe is accelerating. And so we believe that once again nothing is becoming the most important source of energy in the universe and causing the expansion of the universe to accelerate. Okay, wild idea number 4, which may be the wildest. That actually, every time we make a quantum mechanical measurement, and it doesn't have to be you or I, quantum mechanical measurements can be made all the time, the universe splits into parallel universes. So for example, many of you have heard of Schrodinger's cat. Here's a cat, it's in a box. We put the cat in the box. Inside the box is some poison gas. Well, a capsule of poison gas, but it's inside the capsule and the cat is fine, unless a radioactive decay happens and triggers the capsule to open. But we close the box, and when we do that, there's the cat in there, and the question is the cat alive or dead? Okay. And the quantum mechanical answer is, well, this is a cat. It's not really, quantum mechanics doesn't really apply to this cat, for a cat. But suppose this was a quantum mechanical cat, and we were really, really careful about how we prepared this box. Then the cat would be both alive or dead. We open the box. We make a measurement on the cat. The cat is now either alive or dead. What's actually happened is that the universe is split into 2 separate universes, in one of which the cat is alive, in one of which the cat is dead. Most of us think this is an absolutely crazy idea and almost certainly wrong, except that it's also how many of us think about how the quantum mechanics works in the universe all the time. So these ideas are developed and defended by eminent and famous scientists. The one who you've heard most about is, I talked about something called the Hartle-Hawking no-boundary proposal. You've heard the name Hawking. But lots of famous scientists, they are still sheer speculation, and at most one, and probably, not possibly, probably none, is fully correct. Why do we think about these things? Well, because they confront the really outstanding question of fundamental physics, which is, how do quantum mechanics, a theory which has been incredibly well tested, applied from all sorts of to all sorts of things incredibly successfully? We're using it right now. Here I go. I just used it. Right? I'm using it to run this computer. I'm using it to detect the light. The plants outside are using it. Well, it's probably dark now, but before they were using it to do photosynthesis. Okay? Quantum mechanics get used all the time. We understand the theory of quantum mechanics incredibly well. It's incredibly successful. And there's another theory, general relativity, Einstein's theory of gravity, an incredibly successful theory. Every time you use your GPS, you use Einstein's theory of general relativity. We do not understand how they fit together. And quantum cosmology is one of the few laboratories we have where we can think about how putting the 2 of those things together might happen. Thank you.
This lecture is part of the Origins Science Scholars Program of the Institute for the Science of Origins, a partnership of Case Western Reserve University and the Cleveland Museum of Natural History. It has been brought to you with the generous support of Richard Morrison and the assistance of Case Western Reserve University's College of Arts and Sciences, MediaVision, and WVIZ PBS and 90.3 WCPN IdeaStream. For more information on the Origins Science Scholars Program, including a full video archive, please visit the Institute's website at www.case.edu/origins.